All right, good morning and welcome to Lecture 9. Today we're going to start talking about binary search trees. We touch on binary trees at the end of CSE 215, so some of you may have heard some of this build up in fall quarter, but we're going to start from scratch and just dig into this notion of binary trees. And binary trees are really kind of the main data structure that we're going to work with in 222. I mean, we work with a lot of other structures, but a lot of them come out of the ideas of binary search trees. And I'd like to start by motivating our discussion by looking at order of efficiency. So our general setup is we have a bunch of data and we're bringing it in maybe one piece at a time, maybe a set of numbers, and we want to store that data inside the computer. And we know we can do that with an array. We can just, set up an array with a bunch of space, and each time we get a new number, we can just store that number in a new location. And so with an array, we can insert, and it's an order one operation. It doesn't matter if there's 5 things in this array or 5,000 things in this array. If we've got a new number that we want to store, we just drop it in the next available location, and we keep a variable which tells us how much stuff is in the array, and that variable we can use as an index to store a new piece of data. So inserting into an array is an order one operation. And if we want to delete from an array, well, if we just delete from the middle and we try to move everything down to fill up that space, that's an order n operation. If we don't fill up that space, if we just set a flag saying that's deleted, we're going to run out of memory eventually. But if we want to delete something from the middle of the array, and we don't care about the order in which things are stored, we can simply take that thing and replace it with the last element and, shrink our array by one element. That's going to be an order one operation also. So if our array is unordered, if there's no particular arrangement to the data, insert and delete is very efficient. But if we search, well, if there's 5,000 numbers in here and we're looking for a particular number, really the only thing we can do is start at the beginning and check each entry. And the more data we have, the more time that takes, so our search is order n. Now, we can improve this by playing high-low. If we have a sorted array, we know that our search time can become log n. In other words, if our array is sorted from smallest to largest, and we have 5,000 things in this array, instead of just starting at the beginning and searching each one, we'll first search right in the middle. And if the number that we're looking for is smaller than that number in the middle, we can ignore the second half of our array and just check the first half. So after one operation, our problem size is half of what it was. So now we have 2,500 numbers to search, and we can search right in the middle of that smaller array. And if the number we find there is too small, we can throw away the first quarter of our array and just search that second quarter of 1,250 elements. And so each time we do an operation, the size of our problem gets cut in half. And so this is characteristic of a log n operation. So if we increase our amount of data by 1,000,000, our search time will go up by 20. Right? So this is a very efficient way to search. But when we want to insert or delete, we can't just add our new number to the end or delete a number in the middle and replace it with the last number. We need to make sure that the array is always sorted. Otherwise, we can't play this high-low. So if I've got n pieces of data in my array, and I want to insert something new, say right here between the second and third, I'm going to have to move all this other data down one spot to make space. And so insert and delete become order n. So arrays, we have this trade-off. If we don't care about search speed, we can add and delete very quickly. But if we want good search performance, our insert and delete goes down. Well, we can do better with a linked list. So a linked list, remember, we have a set of nodes, each one pointing to the next. And if we want to insert or delete from here, even if this is ordered, so if this is an ordered linked list, let's say all our numbers are stored from smallest to largest, so I don't know, 2, 10, 23, 45, 66, and we want to insert, I don't know, the number 20, right? We create a new node. We take the previous node and point to 20. We take the 20 and point to the next node. And once we know where we want to insert and delete become order 1. So we can have an ordered linked list and our insert and delete remains order 1 instead of jumping up to order n. But unfortunately, we can't play high-low on a linked list. We always start at the beginning, the node the sentinel points to, and we just follow from node to node. And so if we've got n nodes and we're looking for a piece of data, this is going to be order n. And that's a problem. So what we're going to do with a binary search tree is we're going to get the best of all worlds. We're going to have something like a sorted linked list, and our insert and delete are going to be order 1, but our search is going to go back to order log n. And we're going to do that by thinking about how do we play high-low on a linked list. And it's a fruitful exercise. So let me make a linked list, and we'll have sorted data. So there's a linked list of 7 numbers. And we know that normally, our sentinel points to the beginning, and we just follow along. If we wanted to play high-low, what we'd really want to do is search the number in the middle of the list. So instead of worrying about where the first node of the list is, we're going to have a pointer which gets us right to the node in the middle. And I'm going to call that pointer root. Alright, so I'm searching for a number. I go to the root of this list and I say, okay, the number in the middle is 21. If I'm looking for a number bigger than 21, hey, I can ignore half of my list. I can totally toss all that out. And now instead of searching 7 things in my list, I'm only searching 3. If 21 is bigger than what I'm looking for, I can ignore this, and now I just have to search this small list of 3 things. And of course, if I'm looking for 21, I got lucky. I found it right there at the first thing I checked. So we go from 7 elements in our list to 3, either those 3 or those 3. All right, well, we want to keep doing this. We don't want to search these 3 elements just by starting at the beginning. We'd like to be able to start in the middle of this list or in the middle of that list. So we also need a pointer to that 66 and a pointer to this 5. And where should we put those pointers? We're going to store them along with this 21. So this 21 is going to have a pair of pointers. We're not worried about the number that comes after it. What we want is a pointer to the middle of the list to the left of 21 and a pointer to the list middle of the right of 21. And 66, there's a list to the right. Well, it only has one thing, but we're going to have a pointer to the middle of that list, which is the 73, and the middle of this, and the middle of this, and the middle of that. So this is going to be our new data structure. And each node is going to have a number, or whatever type of data we're looking for, but also a pair of pointers. Pointer to the middle of the list on the left, pointer to the middle of the list on the right. And so let me do this in a more abstract way. So here's my data. It's increasing from left to right. here's going to be my root. And the middle of the list on the left, I'm going to point to that. And I'm going to point to the middle of the list on the right. And then this node here, I'm going to point to the middle of the list on the left and the list on the right. And the same thing here. And then this node, I'll point to the middle of the list on its left and its right. Like this. So each node has a pair of pointers and a piece of data. And so we've got this, kind of spaghetti ball of pointers, arrows pointing to other nodes. But the idea is this lets us play high-low on a list. We start right here. This is the middle. If the thing we're looking for is bigger than this, we're going to ignore the left side of our original list. We're just going to search this list. And how do we search this list efficiently? Well, we start with a node right in the middle. How do we know where that is? Because our root has a pointer to it. So we start on this middle node, and if that number is bigger than what we're looking for, we're going to ignore all of that. Just search this small list of 3 nodes, and we want to start in the middle. And how do we find the middle? Because this node that we went to has a pointer to the middle of this smaller 3-element list. So this will let us play high-low. This will let us do an order log n search operation. And as you might be suspecting, this is going to be very recursive. Because we're doing the same thing over and over again, but we're working on smaller problems each time. And this is the hallmark of the recursive problems we did the last time, right? When we write a recursive formula for multiplication, it only works because when we call the multiply function inside itself, we call it on a simpler problem. Well, when we call the search algorithm on this tree, we're going to have to ultimately search this list, but this is a smaller list. So this is going to work really well recursively. So let me take this tree, this list that we've drawn, and draw it a little differently. So here's going to be the root. And this arrow pointing to this node, I'm just going to draw that as a line. And this arrow pointing to this node, I'm just going to draw that as a line. So this circle is that node, and this circle is that node. And this circle has a pair of lines, one going to the left, one going to the right. And there's a node on each of those. And then this node right here, this is this one, has something off to the left and something to the right. And so this is another way to represent this information up here. The implication is when we move down the page, that's the direction of our arrow. So the root is sitting up here, and the things it points to are here and here. This is the middle of the left list, this is the middle of the right list. And so this is a binary tree. It's tree-like, but it's actually upside down, right? A normal tree that we find, the root is sitting at the bottom, and as you go up away from the ground, the tree branches out and gets more and more branches the further up you go. So we always draw our trees upside down, just because we kind of work top to bottom when we write on paper. So there's the root, and the tree gets wider and fluffier as we move down. And so let's talk a little bit about trees abstractly, and then we'll start looking at how we can implement these in code, and then we'll start coming up with some algorithms for operating on binary search trees. Alright, so binary search trees, we have a single root. Every node in the tree has either 0, 1, or 2 children. And we identify these by left and right. So if this is our root node up here at the top, this is the root's left child, this is the root's right child. And every node has a parent except for the root. So this node has a parent, which is here. This node has a parent, which is also there. And maybe this node has a left child, and this one has a right and a left. And so this node's parent is this node labeled L. This node's parent is the node labeled R. This node's parent is also the node labeled R. There's grandparents. All three of these nodes, their grandparent would be the root. So nodes have children, and you could have 0, 1, or 2 children. This node, for example, has no children. This node has no children. Maybe this node has one child on the right. So a node with no children is called a leaf node. And again, if you flip the tree upside down, right, the leaves are the topmost part with nothing coming out of them. So that's a leaf node. This is a child of that node. That node is a parent of the child node. And we use left, right to designate which half of the tree we're on. The binary part means 0, 1, or 2 children. We cannot have a node with 3 children. If we did, it would be a trinary tree. So we're only going to deal for now with trees that have at most 2 children. And an important thing to recognize is that if I pick any node in the tree, for example, this node right here, that itself is the root of an entire tree. This thing I've just circled is also a binary search tree. And this node that I circled, that's the root. This is the left child, this is the right child, this is the right grandchild, and so on. And in that tree, I could, think about this node right here, and that is the root of this little tree containing 2 nodes. So trees are comprised of trees, and any node that we pick in a tree is the root of an entire tree on its own, what we can call a subtree. And this kind of notion is why recursion is going to make so much sense when we start processing our trees. All right, so in general, we'll draw a tree like this. Let me put some numbers in here. So there's a random binary search tree. And 20 is the root of the entire tree, 40 is the root of this subtree, 45 is the root of this subtree, 43 is the root of that subtree. So trees contain trees. So when we talk about a BST, binary search tree, the one thing that makes it different from just a plain old binary tree is the following. So if R is the root, all data to the left of R is smaller than R's data. And similarly, all data to the right of R is larger than R's data. In other words, here's our whole binary search tree. The root is 20. Now we know if we go to the left, this whole thing is a subtree in itself. To be a BST, every number here has to be smaller than 20. And every number here has to be bigger than 20. That's what makes it a binary search tree as opposed to just a plain old binary tree. And that property is true everywhere in the tree. So if I look at this 40 right here, the left tree looks like this. Everything there should be smaller than 40. The right tree is all of this. Everything there should be bigger than 40. Everything here is smaller than 45. Everything there is bigger than 45. Here's a little tiny subtree with a root of 43. The left subtree, everything should be smaller than 43. The right subtree, everything should be bigger than 43. And that property has to be true everywhere in the tree. Here's a 15. The left subtree is this node. That should be smaller than 15. This should be bigger. All of this should be bigger than 10. All of this should be smaller than 10. Alright, so that's a really, really important point to keep straight in a binary search tree. If you pick any node in the tree, everything to the left is smaller, everything to the right is bigger. And that's going to make it feasible to do recursion and do things like search our tree for data very efficiently. So let's look at some algorithms for manipulating BSTs. So we can keep working with this tree right here, and suppose I want to look for the number 17. Well, we begin at the root. The root's the only thing we have access to. And the root is 20, and we're looking for a 17. Is there any reason to check any of these numbers to look for a 17? No. Why? Because 17 is smaller than 20, and in a BST, everything to the right is bigger than the root. So we know everything over here is bigger than 20. We can ignore it, right? We're playing high-low. We said, is your number 20? And the person said, no, it's smaller than that. We don't have to think about any of these numbers anymore. We just have to search this tree. So we come down to this 10. And we say, okay, is your number 10? No, I'm looking for a 17. 17 is bigger. I can ignore the root and everything to the left. And now I come down to the 15 and I'm looking for a 17. 17 is bigger. I can ignore the 15 and the 13. I can come to the right and say, is that a 17? Yes, it is. We're done. So how many operations did I have to do? I had to compare to this, 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 and this. 4 operations. But I have 14 pieces of data in my tree. I didn't have to do 14 comparisons, though. I only had to do 4. Suppose I'm looking for a 16. Smaller than 20, bigger than 10, bigger than 15, smaller than 17. If there was a 16, it would be off here to the left, but there's nothing to the left of 17. I can immediately say 16 is not in your tree. So this is this divide and conquer behavior we get when we cut things in half at each operation. If I want to find the number 43, it's bigger than 20. It's bigger than 40. It's smaller than 45. Hey, there it is. There's my 43. So instead of moving through a big long list starting at the beginning, checking every single thing, we're moving down this tree-like structure, and each time we move down, we throw away basically half the tree. And so the amount of work we have to do is really bound not by how many pieces of data we have in the tree, but how many steps we have to go down until we either find our number or we get to a leaf node. If we get to a leaf node, like we're looking for 41, and we get down here, 42, and that's not our number, and there's nothing to the left, that's when we can say, hey, 41 is not in our tree. And so this is all going to be order log n. And remember, when we say log n, we really mean log base 2. That's sort of the only log we talk about most of the time in computer science. But log 2, log e, log 10, they're related by a scaling factor. So it's the same order of complexity. Alright, so that's the basic behavior of binary search tree, and that's our search algorithm, right? Just start at the root and keep moving down. So if we want to insert into our tree, we do the same thing as when we search. So let's say we want to add 14. Well, we're going to start at the root. 14 should go to the left. There's a 10, 14 should go to the right. There's a 15, we should go to the left. There's a 13, we should go to the right. There's nothing to the right. That's where we put the 14. And we're done. And we've still got a binary search tree. And next time we search for a 14, we'll say too small, too big, too small, too big. Hey, there's our 14. So if you want to add a 49, start at the root. 49 is bigger. It's bigger than 40. It's bigger than 45. It's smaller than 50. There's nothing to the left to go to. That's where we put our 49. If we want to add a 21, well, start at the root. 21 is bigger than the root, so go to the right. It's smaller than 40, so go to the left. 21 is smaller than 32, so we should go to the left again. There's nothing to the left. That's where we're going to add our 21. That's the whole insertion operation. So we simply start at the root and we move down, left or right, by comparing what we're inserting to each node's value, until we get to a point where the node has no child in the direction we want to go, and so we add a child in that direction, and that's where our new node goes. And so we can keep adding to this tree, and it'll always be a binary search tree as long as we're doing this. Alright, the next question is, how do we look at the contents of a binary tree? So let me make a little tree here. So there's a tree containing 7 pieces of data. And there's a number of ways we can traverse or visit each node in this tree. So traversing a tree means traveling through the tree, visiting each node exactly once. And typically, as we visit each node, we're going to print out its value. So suppose we wanted to see the contents of this tree. All we have is a pointer to the root, right? And from the root, we could go left or right. Well, we could certainly print the root and print root's left child and print root's right child. But then we need to print root's left child and root's left right child and root's right left child and root's right child. And if there's deeper nodes, we would need to print root's right left child. And we don't want to write a bunch of statements like that in C, right? Our code would get arbitrarily complex. What we want to do is somehow loop, and in our loop, get through all of the possible nodes in this tree. So this process is called traversal, and it just means traveling through the data in the tree. And I want to describe 3 main ways of traversing a tree. And the first is going to be called in order, and it's also called LNR. And the way we traverse or travel through a tree using in-order LNR traversal is really simple to describe. It's a little hard to understand sometimes, but it's pretty simple to describe. We're going to do 3 things. So this is LNR traversal. First thing we're going to do is an LNR traversal of the root's left subtree. So remember, our root is up here at the top. We don't usually label it. It's just the one node sitting at the top with no parent. So the first thing we're going to do is we're going to do this traveling on the entire left subtree. And then we're going to print the root's data. So we print out the 20 at that point. And then we're going to do an LNR traversal of the root's right subtree. So this is recursive. How do we travel through our tree? Well, first travel through the smaller tree, then print out the root node 20, and then travel through that smaller tree. Well, the recursion is, in step one, when we're saying let's do a left node right traversal of this tree, well, that's a recursive algorithm, which says first we're going to traverse this tree, and then print out the root data 10, and then traverse that tree 15. And how do we do a traversal of this tree containing just a root node 5? Well, we're going to say traverse its left subtree. Well, its left subtree is null, so we don't have to do any work. And then we'll print the root node's data, which is 5. And then trying to traverse the right subtree, while the right subtree is null, so we don't do anything there. So let me put one extra condition in here. So if tree is empty, then you're done. Don't have to do anything. So if the tree is empty, we don't have to do any work. There's nothing to print. Otherwise, traverse the left subtree, print the root data, traverse the right subtree. Alright, so what would this look like trying to traverse this tree? Let's just pretend we're a computer. So first thing we're going to do is traverse this, and then we're going to print a 20, and then we're going to traverse that. Alright, how do we traverse this tree? Well, first thing we're going to do is traverse this, and then print a 10, and then traverse that. And how do we traverse a tree containing just a 5? Well, first we're going to traverse the left subtree, but the left subtree is empty, so there's nothing to do. And then we're going to print the root node data, which is a 5. And then we're going to traverse the right subtree, and the right subtree is empty, so there's nothing to do. So when we traverse this tree, this is what we end up printing. Now we're trying to traverse this 3-node tree. Our first step was to traverse this. Our second step is to print the root node data. And our third step will be to traverse this subtree. And again, to traverse this, we'll say, okay, first traverse the left subtree. Well, the left subtree is empty, nothing to print. And then print the root node data. And then traverse the right subtree, which is empty, there's nothing to print. So when we traverse this circled tree, this is what we will output. Now to traverse our original tree, we said we do 3 things. First we traverse this subtree, that produces that output. Then we print the root node data. And then we traverse the right subtree. So we got to do this all again. Well, how do we traverse this? First we're going to traverse this, then print a 40, then traverse that. And to traverse this tree, first we'll traverse the left, which is empty. Then we'll print the root node data. And then we'll traverse the right, which is empty. That completes traversal of this tree. Now we print the root node, which is 40. And then we traverse the right subtree, which is a 60, nothing on the left. Print the 60, nothing on the right. That completes the traversal of this, which completes the traversal of the original tree. And there's our data. Not coincidentally, our data is in increasing order. Alright, when you've got your brain around this, you are in good command of the notion of recursion. This is quintessential recursion. This is classic. And it's one of the harder algorithms to kind of wrap our brains around. But once you start making peace with this, you're in really good shape towards making peace with recursion. So if someone hands us a tree and says, hey, what's the LNR traversal look like? We don't necessarily go through all of those steps that I went through. We start shortcutting. And we could imagine that, maybe I had a tree with a 0 up here. And the right subtree looked like this, and on the left I had, a -10 and a -15 and a -2. And if this was the tree I wanted to traverse, well, I would have to traverse this entire left subtree, and then print a 0, and then traverse this right subtree. Well, that last step, traversing the right subtree, would produce all of this. And right before this would be the 0, the root, and right before that would be the traversal of this left subtree. Because it's a BST, this left node right traversal is guaranteed to give you your data in order. And you can prove that. And you could prove it using a proof by mathematical induction. And the proof would be pretty straightforward to write. because the reason that traversing this entire subtree gives you your data in order is because traversing each of those smaller trees also gives you your data in order. And everything here gets printed first, and that's smaller than the root, and everything here gets printed last, and that's bigger than the root. So you're going to print the smaller stuff, the root, and the bigger stuff. And as long as traversing these subtrees gives you everything in order, traversing the original tree will give you everything in order. So again, if you've done 215, or if we're thinking about mathematical induction in 215, you can start tying together some of these notions of mathematical induction and recursion, and they really are the same beast. All right, so this is in order traversal, LNR, left node right, and it gives you your data in increasing order. Now, we don't normally talk about this, but if we were to do right node left traversal, where we said traverse the root's right subtree, print the root data, traverse the root's left subtree, that would give us our data in decreasing order. But we don't usually do that. Usually we're just going left node right. But there are two other traversal orders that are still interesting to us. And so these are called NLR, which is pre-order, and LRN, which is post-order. So if we go left node right, which is in order, we know that's going to be 2, 5, 7, 10, 15, 20, 30. Node left right says first we print the root node, then traverse the left, then traverse the right. So for this tree, node left right, first we would print the 10, and then we would traverse the left subtree. And to do that, first we would print the root node, and then the left subtree and the right subtree. That completes traversal of the left, and then we traverse the right subtree. First we print the node, and then the left, and then the right. So that's node left right pre-order, and left right node says, okay, first traverse the left subtree, then the right, and then print the root. So the 10 is going to be the last thing we print. How do we traverse this? First print the left subtree, and then the right, and then the root node. And then traverse this, first do the left, the right, and the root node, and then finally do the root of the original tree. And we want to know how to do these, but we don't usually do those too often. There's cases where this pre-order will be useful for parsing expressions, but mostly we do in order, left node right. But if you can write the code to do an in-order traversal, it's trivial to change it to do pre-order or post-order. And the algorithm, for example, node left right of a root is pretty straightforward. So if root is null, return. So if there's nothing in the tree, we don't have to do any work. Otherwise, first print the root data, and then do our node left right traversal on root's left subtree, and then do our traversal on root's right subtree. And that's node left right. If we want to do left right node, just move this print statement to the end. And if we want to do in order left node right, put this print statement right in the middle. So the algorithm is almost the same. It's really just the order in which we do the traversals and print the root data. And it's named pre-order, post-order, in order for where this node data is printed. If it's printed first, that's pre. If it's printed last, it's post. If it's printed in the middle, it's in order. So there's three ways to traverse trees. And the code we can write looks almost exactly like this algorithm. All right, so let's look at how we actually store this information inside a program, inside the computer. Let's look at how we would structure our data to create nodes and put those nodes together to make a binary search tree. All right, so let's play with some code. Let's make a tree.c. And I'll pull in my list code just to get us started. So we've got standard I/O. We'll have standard lib because we're going to allocate nodes on the fly. And let's think about our tree node structure. So this is going to be our node for a binary tree. It's going to be a binary search tree, but same node structure. So I'm going to define my node as follows. I'm going to still just assume integer data. Our data could be anything. Could be strings, integers, WAV files, movie files, whatever. I'm just going to use integers for simplicity. And then I'm going to have a pair of pointers, one which points to the left and one which points to the right. So it points to the root of the left subtree, and this points to the root of the right subtree. And we're going to build our tree up out of these nodes. And we're just going to do this by hand. So I'm going to say struct node tree. I'll call it root. All right, so we're just going to do this, line by line, and of course later on we would bundle this into, different functions that could be called and so on and so forth. But for now, we're just going to just do this line by line in a C program. So let's construct a root. Alright, so there's the root of our tree. So again, we use size of, always use size of on a type of variable, in this case a struct node, and allocate that much space. And so root is this thing that should have a pair of pointers. So root we can think of as a box with a data field and a left field and a right field. But we'll more often think of it like this, right? Root with a left and right child. And I'm going to make a pair of nodes. I'm going to make a node called node 1 and another called node 2. I'm going to put these on the left and right. So let's make some new nodes. And let's get rid of our comments. All right, so see, I can declare my variable here and then give it a value in a separate line, or I can declare and initialize in the same line. Those are both legal. And so N1 is another node, N2 is another node. And let's give these things some values. So I'm going to imagine that my tree looks like this. Let's put a 10 up here, and let's put a 5 down here, and a 15 over here. Alright, so I'm going to say root arrow data equals 10, N1 arrow data equals 5, N2 arrow data equals 15. Right? So root node is 10, left is 5, right is 15. Now we would normally be doing this, while we're reading data in from a file or something like that, but we can imagine that we're just getting these, just storing these, by hand, so that we have something to work with. So left node has a value of 5, right node has a value of 15. let's connect these nodes to each other. So remember, n1 is a pointer. The arrow says follow the thing it points to. That should be a struct node. Let's take the data field. That's this integer, set it equal to 5, or set it equal to 15, or in the root set it equal to 10. So if we want our root to point on the left to n1, all we've got to do is the following. So let's say connect these nodes. Root arrow left equals n1. And it's this simple because n1 is a pointer. n1 is the address of this struct node. It's the address of this node containing a 5. And root 1 arrow left says root 1's a pointer, follow it to a struct node. Let's look at the left field. Well, what is the left field? It's a pointer to a struct node. It's the address of a struct node. And what do we set that address to? We set it to n1, which is the address of a struct node. So this is where pointers stop being such a pain. Because if we make everything a pointer, we get to stop thinking about them as pointers. We can just think of them as the nodes themselves. And even though this is a pointer, we don't have to think of it. We can think of this as the left node of the root, and we can think of this as that node itself. And so we can say something like root arrow right equals n2. And that says, okay, root on the right should point to n2. And we can build up a little more of a tree. So I could do something like this. Let's make another set of nodes. Let's make an n3 and an n4. And let's hang those down here. So here's going to be n3, here's going to be n4. And I don't know, we could make this a 12, and we could make this an 18. So I'm going to say n3 data equals 12, n4 data equals 18. And then I can say n2 left equals n3, and n2 right equals n4. All right, so n2 points to n3 and n4. So n2 points to n3 and n4, and that's all sitting on the right of the root. So this should nicely construct by hand, right, just line by line, a nice little tree containing 1, 2, 3, 4, 5 pieces of data. And so let's go inside GDB and let's just get some practice dereferencing these pointers and looking at what our tree looks like. So let me go ahead and end our program. And I'll compile with a G switch. Got an extra flag there. There we go. So I can say GDB tree, hop into the debugger, and now I'm ready to start executing my code line by line. Alright, so I'll say start to begin the debug process, then I'm just going to next my way through each of these statements. So we've created our small tree, we've tacked on the left and right nodes. And so before we add on these extra n3, n4s, let's just take a look at our tree right now. If we print root, it's just, you know, a number, but it's a pointer to a struct node. So if we say print star root, hey, it's a node with a data value of 10, a left child of this, and a right child of this. So if I print star root arrow left, that says start at the root, go down to the left. We know that's a pointer to a struct node. Show me what that struct node is pointing to. And that's a node with a data value of 5 and left and right children being null. And if I print root arrow right, that's a node with a data value of 15 and left and right children being null. So we've constructed this little tree here with a root, 2 children. But now we can go ahead and we can do these extra statements. Let's make a node n4 and N3, let's set their data values. Let's hook them up to node N2. And now if I print root arrow right, it's still got a data value of 15, but its left and right children are not null anymore. They exist. And if I print root arrow right, arrow left, that's a node with a value of 12 and no children. That's this node right here. So root arrow right, arrow left gets me to the 12. And if I do root arrow right, that should get me to the 18. So let's do root arrow right. There's our data value of 18. So that was a long setup, but once we've got this set up, it gets really, really easy and comfortable to start working with this code. And our statements, you know, start looking kind of what we would hope they would look like, where we can just say things like, you know, node 2's left child is N3, node 2's right child is N4. N4's data is 18. And so this is where this arrow notation lets us stop thinking about pointers and just kind of start thinking about the data itself. And that's what we want to be able to do with data structures, right? Concentrate on the data, not worry too much about the code, right? Think about how we want to organize our information, and we've already got the tools and the experience to write the code to use whatever whatever approach we decide is most appropriate. All right, so we've created a little tree in memory, and in the practice problems today, you'll get to repeat this exercise, but also start writing some code for manipulating the structure further. And the main thing we need to know is that, you know, if we have a root of a tree and we want to get to the left subtree, it's just root arrow left. If we want to get to the root node's data, it's just root arrow data. And so our in-order traversal might look something like this. Let me call it the right thing. Left node right, struct node, star root. All right, if root is null, return. Otherwise, do our traversal on root arrow left. And this, you know, is exactly the C code we would write. Make the function call on root arrow left, and then print root arrow data. Well, that's pseudocode. We need to say printf, you know, quote %d, etc. And then this is also C code. Do the left node right traversal on root arrow right. And so our C code for doing in-order traversal is going to be 4 lines. Base case, check to see if the root is null. If it is, don't do anything else, just return. And then the inductive step, traverse the left subtree, print the root data, traverse the right subtree. And so we'll do similar things for the other algorithms for searching and for inserting into a tree. So practice problems to work on all of those, but this is very similar to what a lot of our code is going to look like, right? And the main thing is just knowing how do you get to the data field, how do you get to the left and right fields. All right, searching a tree is going to be similar. If we want to search a tree for a given piece of data, we might make a function like this. So we'll pass the root of our tree and a piece of data we're looking for. And we could say if root data equals data, return 1, because we found it. So I'm writing pseudocode here, so use a double equal sign for comparison. If the root data equals our data that we're looking for, we found our data, return a 1. If data is less than root data, what do we want to do? We want to search the left subtree. If we're searching for a number and it's smaller than the root, just search the left subtree. If it's found in here, it's found in the original tree. If it's not found in here, it's not found in the original tree. So if our data is less than the root data, we can just say search root left for that data. And whatever that returns, that's what we should return. Right? We'll just repeat whatever we got from that search. So call the search function. If it gives you back a 1, return a 1. If it gives you a 0, return a 0. Otherwise, we know data is bigger than root data. And so we can return search root right and data. But if I run this code, I will segfault. And the reason I will segfault is because I don't have a base case. If I'm searching for a number that's smaller than my root, it's not at the root value. It's going to be less than the root. It's going to search the left subtree. Well, suppose I'm searching for the number 0. Smaller than this, so I'll search this for the number 0. Smaller than 5, I'll search this for the number 0. Smaller than 2, I'm going to search the left subtree of 2 for the number 0, but the left subtree is null. In other words, this root arrow left would be null, and I'll make a call to search where my root is null, and now I'm going to be searching null, comma 0, and as soon as I say null arrow data, I'm going to segfault. So this code works perfectly, except if the root is null, it will blow up. But that's not a problem, because if the root is null, we already know the answer. If the root is null, return a 0. Because obviously our data is not in the tree if there's nothing in the tree at all. And it's interesting to note that this is the only statement in this entire function that ever returns a 0. We have a statement that returns a 1. We have some recursive calls. But without this statement, there's nothing in here that would ever return a 0. That's another clue that we're missing a statement. So there's our base case. If the tree is empty, return a 0. Otherwise, if it's at the root, return a 1. Otherwise, do some recursion. So that's a search function. Insert's going to be a little more interesting. And the practice problems dig into some detail on this. So you'll actually go through step by step making a function to do insertion. But the trick with insertion is that if we start with an empty tree, like root equals null, and we say insert root comma 10, well, if root is null and we call insert root comma 10, root is still going to be null when we come back. Remember, everything in C is passed by value, so insert cannot change the value of root. Root is null, make this call, when we're done, root is still null. So when we are calling functions that are going to modify our tree, we're generally going to have our function return the new root of the tree. And so our insert function would be something like struct node star insert struct node star root integer data. And then somewhere in here we're going to return whatever ends up being the root of our tree after we've done the insert. So the problems will take you through some of those details and ask questions in class. So those are our basic algorithms for traversing the tree, searching the tree, inserting into the tree. And once you've got those, you're on top of trees, right? We'll have one more nasty algorithm to talk about next lecture, which is deleting from a binary search tree. But concentrate on these, get these down, and you'll be in really good shape. All right. That's good enough for now. Go ahead, work on the problems, and we'll go on to tree deletion and also height and balance in the next lecture.